scientists have found the strongest evidence yet that a black hole and a neutron star collided while moving along an oval-shaped orbit, instead of the near-perfect circles scientists usually expect before such mergers. The discovery challenges long-standing ideas about how these extreme cosmic pairs form and evolve. Astronomers generally expect neutron star and black hole pairs to settle into circular orbits long before they merge. However, a fresh analysis of the gravitational wave event GW200105 revealed that this system was still traveling on an oval-shaped path shortly before the two objects combined. The merger ultimately produced a black hole about 13 times the mass of the Sun. Detecting such an oval orbit in this type of event has not been reported before. Researchers said that this discovery gives us vital new clues about how these extreme objects come together. It tells us that our theoretical models are incomplete and raises fresh questions about where in the universe such systems are born. To investigate the event, researchers studied data from the LIGO and Virgo gravitational wave detectors using a new model developed at the University of Birmingham's Institute of Gravitational-Wave Astronomy. This approach allowed researchers to measure how stretched the orbit was, eccentricity, and determine whether the system showed spin-related wobbling, precession. It is the first time scientists have measured both of these effects together in a neutron star black hole event. The orbit gives the game away. Its elliptical shape just before merger shows this system did not evolve quietly in isolation, but was almost certainly shaped by gravitational interactions with other stars, or perhaps a third companion. Researchers performed a Bayesian analysis that compared thousands of theoretical models with the actual gravitational wave signal. Their results show that a circular orbit is extremely unlikely, ruling it out with 99.5% confidence. Earlier studies of GW200105 assumed the orbit was circular. Because of that assumption, they underestimated the mass of the black hole and overestimated the mass of the neutron star. The new analysis corrects those measurements and finds no strong evidence for precession, suggesting the oval orbit likely originated during the system's formation, rather than being caused by spin effects. This is convincing proof that not all neutron star-black hole pairs share the same origin. The eccentric orbit suggests a birthplace in an environment where many stars interact gravitationally. The findings challenge the widely held idea that all neutron star-black hole mergers develop through a single dominant formation pathway. Instead, the research suggests that multiple formation scenarios may exist, some shaped by crowded stellar environments where gravitational interactions are common. The study also helps explain the increasing variety of compact binary mergers observed through gravitational waves. As detectors continue to identify more events, astronomers expect to uncover additional unusual systems that reveal new routes by which these powerful cosmic collisions occur.